We start our discussion on the last module, module number 3 of chapter 1 now. In the last module, we have defined some special types of sets called Lebesgue measurable sets. We have already seen that the empty set and the whole real line, the whole set R are both measurable. A set E is measurable if and only if E complement is measurable. The collection of all Lebesgue measurable sets is closed under difference and countable union, that is, it forms a sigma algebra. We have also seen some concrete examples of Lebesgue measurable sets, like we have shown that if a set E has Lebesgue outer measure 0, then it is Lebesgue measurable, and consequently any countable set is Lebesgue measurable. In this module, we are going to show you some more examples of Lebesgue measurable sets by showing that many of our known sets from real analysis are actually Lebesgue measurable. We are also going to prove some further properties of these special types of sets. And with this, we go to the first slide of this module. We start with this lemma. We want to prove that open interval A infinity is measurable. Now, we will use the definition of measurability to prove this assertion. Consider any arbitrary A subset of R. Let us write open interval A infinity as interval I1 and its complement, that is open interval minus infinity A closed as the interval I2. See that I1 union I2 is the whole real line. So, what we have to show? We have to show that mu star of A intersection I1 plus mu star of A intersection I2 is less or equal to mu star of A, because we already know that mu star is countably subadditive, and so the reverse inequality is always true. So, the equality will come if we can only show this inequality. Without any loss of generality, let us assume that mu star A is finite, because if it is infinity, then the above assertion is always true. Now, let epsilon greater than 0 be given. Now, recall the definition of Lebesgue outer measure. How we constructed the Lebesgue outer measure of a set A? The Lebesgue outer measure of the set A, mu star A, has been defined as the infimum of all possible values sigma n l I n, where I n is a countable collection of open intervals covering A. And so, if we use the definition of infimum, then for epsilon greater than 0, we can find a countable collection of open intervals J n, n belonging to capital N, such that A is covered by the intervals J n, that is A is subset of union n is equal to 1 to infinity J n, and at the same time the sum of the lengths of J n, that is sigma n is equal to 1 to infinity L J n, this is less than mu star A plus epsilon. Now write Jn dash as Jn intersection I1 and Jn double dash as Jn intersection I2. Now see that I1, I2 are intervals and this Jn are open intervals, and we know that intersection of two intervals is again an interval or it is empty. And since I1 and I2 are already disjoint, so Jn dash and Jn double dash are disjoint. Jn is the union of these two sets Jn dash and Jn double dash, and as we said that they are either empty or an interval. Consequently, from the notion of the length function, we already have this, that L of Jn is equal to L of Jn dash plus L of Jn double dash. Now, let us start with mu star A plus epsilon. We already have that mu star A plus epsilon greater than sigma n equal to 1 to infinity L j n, which is equal to sigma n equal to 1 to infinity L j n dash plus sigma n equal to 1 to infinity L j n double dash, because L j n is equal to L j n dash plus L j n double dash. This is again equal to sigma n equal to 1 to infinity mu star of j n dash plus sigma n equal to 1 to infinity mu star of j n double dash, as we have already proved that for intervals the Lebesgue outer measure is equal to their length, but they are greater or equal to mu star A intersection I1 plus mu star A intersection I2. Why? Because if we consider the set A intersection I1, we already have that A intersection I1 is subset of union n j n dash. So, we can use the countable subadditivity of the Lebesgue outer measure. Similarly, using the countable subadditivity of Lebesgue outer measure on the second set A intersection I2, we have mu star A intersection I2 less or equal to sigma n equal to 1 to infinity mu star j n double dash. So, on the whole we have mu star of A plus epsilon greater than mu star of A intersection I1 plus mu star of A intersection I2. Again, see that the right hand side does not depend on epsilon, and this inequality is true for any epsilon greater than 0. So, since epsilon greater than 0 is arbitrary, we have mu star A greater or equal to mu star A intersection I1 plus mu star A intersection I2, and this shows that our assertion that open interval A infinity is measurable. From this assertion, we get a very important theorem, theorem 4 of this whole presentation, that every open set as well as every closed set in R is measurable In particular, every Borel set is measurable, where Borel sets are defined as the members of the sigma algebra generated by the class of all open sets. The formal definition is given in chapter 9. We have already seen that for any real number a, open interval a infinity is measurable. Now, we know that a set E is measurable if and only if its complement E complement is also measurable. So, the complement of the interval open interval a infinity, that is the interval open infinity a closed, is also measurable, and this is true for any real number a. Now, if we consider any interval open a b closed, where a is less than b, then see that we can write this interval as open minus infinity b closed intersection open a infinity open. We know that union of two measurable sets is measurable, as also the difference of two measurable sets is measurable, and from this we can easily show that intersection of two measurable sets is again measurable, and hence it follows that for any two real numbers a and b, open a b closed is measurable. Now, see that if we consider open interval a b, we can write it as open a b closed minus singleton set b. Now, singleton set b has Lebesgue outer measure 0, so is measurable. So, being the difference of two measurable sets, any open interval a b is measurable. Finally, if we consider any open set, see that any open set is actually countable union of open intervals. So, it is again measurable, because we know that the collection of measurable sets form a sigma algebra, and the complements of open sets, the closed sets, are also measurable. And if we consider the collection of Borel sets, then Borel sets are also measurable, and this follows from the fact that the Borel sets are the members of the sigma algebra generated by the class of all open sets, and the collection of measurable sets is already a sigma algebra containing the class of open sets, and the Borel sets is the smallest sigma algebra containing the class of open sets. We will see this particular result in the chapter 9. So, in view of that result, it follows that every Borel set is also measurable. So, we have many concrete examples of measurable sets, and in fact, most of the known sets which we use in analysis, like open sets, closed sets, F sigma sets, G delta sets, etc., they are all measurable. Finally, the measurability of Borel sets follows from the fact that the collection of measurable sets S, if we name it, is a sigma algebra, as we have already seen, and it contains the class of open sets, and by definition the class of Borel sets is the smallest sigma algebra containing open sets. We can show one more property of measurable sets by showing that if E is measurable, then its translation E plus x is also measurable, and their outer measures or measures are equal. Finally, we will now give an example of an uncountable perfect nowhere dense measurable set whose measure is 0. Why we need this example? Because we have already seen that countable sets have measure 0, but there actually exist many sets which are uncountable, but still which have measure 0. For this, we proceed in this way. Let us take the interval closed 0 1, write it as D1. Let D2 equal to closed 0 1/3 union closed 2/3 1, D3 as closed 0 1/9 union closed 2/9 1/3 union 2/3 7/9 union closed 8/9 1. So, what we are doing? So, in each step we are dividing the intervals into 3 equal parts and we are eliminating the middle open interval. Let us define C as the intersection of all these sets Dn. Then C is called the Cantor set. Now, see that since each Dn is measurable, their countable intersection C is also measurable, and since C is subset of Dn for every n, so mu star C is less or equal to 2/3 to the power n, and as this is true for any positive integer n, and as n tends to infinity, the right hand side tends to 0. So, we have mu star C equal to 0. Finally, that this set C is uncountable follows from the fact that every point of C has a unique representation of the form x equal to r1/3 plus r2/3 square plus plus rn/3 to the power n, and this series is not terminating, and where Ri is either 0 or 2. And we can easily define a bijection from C to closed 0 1, because we know that the elements of closed 0 1 has a unique binary representation of the form x1/2 plus x2/2 square plus etcetera xn/2 to the power n, and which is non terminating. And so, we can define a 1-to-1 map between any x belonging to C and the corresponding element f x in closed 0 1, and this shows that the set C is uncountable. And finally, note that C is also perfect and nowhere dense. Now, we will prove a assertion that if a set A has Lebesgue outer measure 0, then the set of all squares of the elements of A is also measurable. We prove the result by assuming that 0 does not belong to A, and which is sufficient for our purpose, because we only delete at most one point from the set A. Now, write the set of all squares of the elements of the set A as the set B, that is B equal to collection of all x square where x runs over A. Now, for each n belonging to capital N, let us write A n as A intersection open interval minus n n, and Bn as B intersection open 0 n square, because see that B is a set of non-negative numbers. Obviously, B is equal to union n equal to 1 to infinity B n, because the union of all those intervals 0 to n square is the interval 0 to infinity. And since mu star is countably sub-additive, so the proof will be complete if we can show that mu star Bn equal to 0 for all n. So that it will follow that mu star B is less or equal to sigma n equal to 1 to infinity mu star Bn, and the right hand side will be 0, and subsequently the left hand side will also be 0. And we know that a set which have Lebesgue outer measure 0 is measurable. To show this, let epsilon greater than 0 be given. Now, see that mu star of A n is less or equal to mu star of A, because A n is subset of A, but mu star A is 0. So, mu star of A n is 0 for each n. Again, using the definition of Lebesgue outer measure, we can find a countable collection of open intervals I k, k belonging to capital N, such that A n is subset of union k equal to 1 to infinity I k, and sigma k equal to 1 to infinity L I k is less than epsilon by 3 n. Without any loss of generality, we can assume that none of the I k's contain 0 and are contained in the interval minus n to n. Let us write I k as the open interval C k d k for each k. Now, consider the corresponding interval formed by the squares of the endpoints, that is, we consider the interval j k, where j k equal to C k square d k square, if C k is greater than 0, and j k is equal to d k square C k square if d k is less than 0. Now, clearly this countable collection of open intervals j k, k belonging to n, covers B n, and further if we consider the sum of the lengths of the intervals j k, that is sigma k equal to 1 to infinity L j k, this is equal to sigma k equal to 1 to infinity mod C k plus d k into d k minus C k, and this is less or equal to 2 n into sigma k equal to 1 to infinity L I k, and the right hand side is less than epsilon. And this shows that mu star of B n is equal to 0, and this completes the proof of our assertion. So, to summarize, what we have done in this module is that we have first shown that open interval A infinity is measurable for any real number A, and with the help of that fact, we have then shown that any open interval A b is measurable, and consequently any open set being countable union of open intervals is also measurable, as also their complements, that is the collection of closed sets. We have also observed that the class of Borel sets are also measurable, as it is the smallest sigma algebra containing the class of open sets, and the class of measurable sets already forms a sigma algebra containing the class of open sets. So, we have seen that most of the known sets which we have come across in analysis, like open sets, closed sets, are measurable. Also F sigma sets, G delta sets are measurable, as F sigma sets are countable union of closed sets and G delta sets are countable intersections of open sets. So, with these comments we finish this module.